Section 3B, all about the atomic structure. We'll look a little bit more into protons, neutrons, and electrons as we start to learn about what the atoms do, and later on we'll see what the electrons do, particularly electrons we call valence, as they start to combine with other atoms. So notes 3B, the atomic structure. Are we ready? Here you see what we call a Bohr model of a carbon atom. And as you look to the right, you see that this atom has 6 protons labeled with the positive charge and 6 neutrons. We talked about a little bit of what protons and neutrons are in notes 3A. And you add those up and you get a total of 12 subatomic particles in the nucleus, and that's what's going to make up the mass of that carbon atom. 6 protons and 6 neutrons for an atomic mass of 12. And then you see a total of 6 electrons, and in just a little bit we'll talk more about those 2 rings and the positioning of those electrons. 3 basic subatomic particles, they're all pictured on the screen right now. The electron. Put the word in green because you see the green on the Bohr model. Those have the negative charge. We talked a little bit about the 2 kinds of electric charges that the particles have. Electrons have the charge called negative. Protons have the charge called positive. They're found in the nucleus, as you see. Look at the blue with the plus signs on them, the positive plus signs. And then the neutrons have no charge. They are also found in the nucleus. And again, the mass of the atom, we find that by simply adding the protons plus the neutrons. That'll give us the atom's mass. Ready? Now let's look a little bit at these electrons, those green ones with the negative sign you saw on the last page. These have the negative charge. Now, we'll talk later in the year about electrical energy, but it's electrons moving from one atom to the next in a long line of succession that gives us electricity, and we're going to talk about electricity later in the year. Electrons also get atoms to combine with each other, particularly the ones we call valence, and you'll see that on the screen in a little while. Now, these are the smallest of the 3 particles. The protons and the neutrons are far larger than the electrons. Remember the size of a kilogram, which weighs about 2.2 pounds. Now look at an electron. You have 9.1094 times 10 to the negative 31 kilograms. That is a very small number. And that means 91094. I won't write them all out, but if I start here, I'm going to go way out here with all these zeros. This is nowhere near as many. We're actually going to need 30 of those zeros. And that'll tell you how small the mass of an electron is. Extremely small. In fact, so small it's nearly 2,000 times less massive than a proton. As you see the number right here, 1 over 1,836, and we're used to seeing the fractions written more up and down. So 1 over 1,836, the mass of a proton, that is what the mass of an electron is measured in kilograms. Negative charges repel each other. Remember the law of charges. Like charges repel, unlike charges attract. Well, if that's the case and electrons are found in pairs, why don't they push each other apart? Well, that's because they're all spinning, the pairs are spinning in opposite directions so fast that the charge really doesn't have a chance to work on each other. So pairs of electrons, even though they're like charges, can still stay very close together. I mentioned valence electrons just a little bit ago. These are the ones on the outside energy level. Now, I can't draw, but I'll see if I can put somewhat of that model back on the screen that you saw on the last page. There's your nucleus. There's your first energy level for carbon. Carbon has a total of 6 electrons. So 1, 2, 3, 4 on the outside, plus these 2, that makes 6. Valence electrons are the electrons, get that out of the way, on the outside energy level. Now, of course, as we go down the periodic table closer to the bottom, we will add more rings, which means we'll add more electrons, but the valence electrons are always on the outside energy level. I do wish I could draw better, but I can't. But valence electrons, get to know that term because we're going to talk about those things a lot. Those are the party animals. Those are the electrons that cause atoms to combine with each other. Ready? Look at this Bohr model of a krypton atom. Bohr model, remember, is a model that shows the energy levels, the circles, and the electrons on those. Now you see on the krypton, and we're even told over here, that krypton has 2 electrons on the first level, 8 on the second, and remember we always go inside out when we're counting the energy levels. 18 on the third. Now the fourth level, as you'll see on the screen in a moment, can go up to 32, but krypton goes up to 8. And you notice on the periodic table, the last column on the right, except for helium, all of those from neon down will end in an 8. Helium will end in a 2. So if there are levels 5, 6, and 7, then that fourth level right there can go as high as 32. Now let's put that on the screen here. These are the maximums. Remember, not all the levels have all the electrons that you're about to see listed here. These are the maximums that the levels could hold. In this class, we worry mainly about the first 4 energy levels. I'll mention 5, 6, and 7, but we'll focus on 1, 2, 3, and 4. The first level can hold at most 2 electrons. No atom will ever have a 3rd electron on that first energy level. See, I can't even draw it. Of course, I'm being silly about that. But really, you'll never have an atom with more than 2 electrons on the first level. Now remember, hydrogen's way over here, and helium's way over here. And in the next chapter, we'll talk about why that big gap, and then another big gap, and then another big gap in rows 2 and 3. Remember, the rows are called periods. But hydrogen way over here and helium over here, they're in the first row, the first period. They will never have more than 2 electrons on that first energy level. Now, helium's that way always. Hydrogen has to do something that we'll learn about later to get that second electron. The second energy level can hold as much as 8 electrons. You see that on the Bohr model on the screen. So krypton's configuration is 2, 8, 18, 8. Well, on the third level, that one can go up to 18. Now the fourth level, we see only 8 for krypton because that's all krypton has. But you go to periods 5, 6, and 7, the fourth energy level can get as high as 32, but no more. Now we're going to worry about the maximums of just these first 4 energy levels. I said a few minutes ago that I'll mention 5, 6, and 7. Theories for 5, 6, and 7 is that level 5 could go to 50, level 6 could go to 78, and level 7 could go to 92 if the pattern of the first 4 were to continue. Thing is, they don't. They actually go as much as 32 and then back down, and that makes it a little more complicated, and you'll learn more about levels 5, 6, and 7 in higher levels of chemistry class. So in our class, we worry about just the first 4 energy levels as far as the maximums go. First level 2, second 8, third 18, fourth 32. Ready? Now let's talk a little bit about these protons, the positively charged particles in the nucleus. It is the number of protons that will determine the atom that we have. Now remember, protons are positive, electrons are negative. Since they're opposite charges, they're going to attract. The protons are going to draw the electrons in, but again, think more like the planets orbiting the sun. The electrons are also rotating and revolving around the nucleus of the atom, and they're moving very fast, but that electrostatic force that's attracting the protons and the electrons keeps the electrons moving in a circular orbit around the nucleus. Remember, the protons determine the type of element that the atom is. So let's just pick calcium with 20 protons, and there's a reason I'm putting the 20 here. You're actually going to see in just a little bit. But the atomic number is a number of protons. Calcium has 20. If we were somehow to remove a proton, which happens with certain atoms near the end of the periodic table, but that calcium would no longer be calcium because that 20 becomes a 19. And we can see now that we're now talking about the element potassium with 19 protons. Even just that one difference in proton will give us a completely different element. And I think I mentioned this before. Chlorine with 17 protons is a very deadly gas, but argon with 18 protons is a very safe gas that's used in neon lights and in insulation in windows to help keep heat in and out. So one difference in protons can completely change the element from very deadly to very dangerous, or vice versa. Very deadly to very safe, I meant, and vice versa. But the protons determine the type of atom, and the number of protons is called the element's atomic number. All determined by the number of protons. Ready? Oh, the mass. Forgot that line was coming. 1.6726 times 10 to the negative 27th kilograms. Again, almost 2,000 times more massive than the electrons. But these are teeny tiny little bitty guys, so imagine about the electrons as well. Neutrons are almost the same mass as a proton. Ready? Okay, now we are ready. In a neutron, they're also in the nucleus, in there with the protons. The neutrons really don't serve too much of a purpose. They do give the atom mass, and they provide a little bit of insulation. You take an atom of calcium with 20 protons that all have like charges, those things should be repelling. But all the neutrons in the middle of all the protons provide a little bit of insulation, enough so that electrostatic force of repulsion does not affect each other. So the neutrons will give the atom mass and hold the protons in place. Now, a moment ago I said the neutrons have almost the same mass as a proton. In fact, the neutron's a teeny tiny bit more. Really, if we add up the mass of a proton and the mass of an electron, we get the mass of a neutron. And that's why a few minutes ago I said we just add the protons and neutrons to get the mass, because when we do that, we have automatically used the electron. The mass of an electron is so small that if we just say mass equals, let me write that, mass equals proton plus neutron, we're automatically including the electron in there. So we don't have to count the electron. There's no electric charge in a neutron. That's why they're called neutrons, because their electric charge is neutral. Now, all elements of calcium will have 20 protons, but they will not all have 20 neutrons. A few have a little more than 20. A few have a little bit fewer than 20. If the neutrons vary, then what we have is called an isotope, and I'll tell you a little bit more about that in just a bit. But for most of the atoms, the number of neutrons will vary, not stay exactly the same. What that will do is make an atom a little bit heavier. So some calcium atoms are a tiny bit heavier than most of them are, and some of those atoms are a tiny bit lighter in mass than the rest of the calcium atoms are. They can also turn a perfectly stable atom into something a little bit radioactive. But as I said a moment ago, the neutrons will keep the protons from repelling, because they'll provide some insulation to block that repelling like charge electrostatic force. Ready? I mentioned atomic number a little while ago. There's that same carbon atom. We have 6 of those protons. You see 4, the other 2 may be behind the rest of them. And we have 6 neutrons, maybe the 6th one, I see 5, again is also behind those other ones. But the carbon atom, most of them have 6 protons and 6 neutrons. The definition of atomic number is the number of protons in the nucleus. So every element of carbon has 6 protons. The atomic number of carbon is 6. That's the reason carbon is element number 6 on the periodic table. The periodic table is in order by atomic number. Almost all atoms of the same element have the same atomic number. I said almost. Actually, all atoms of the same element have the exact same atomic number. Every gold atom has exactly 79 protons. It's the neutrons that can vary a little bit. If you look at the mass of gold on the periodic table, that decimal rounds off to 197. All I have to do is subtract 197 minus 79, and I get the number of neutrons for most gold atoms. And again, that's coming up very soon. The atomic number is also the total number of electrons, although the definition of atomic number is protons. The protons and the electrons match each other until the atoms start to combine, but a single carbon atom will always be 6 protons and 6 electrons. That's going to give them a total electric charge of 0. Atoms are neutral because the protons equal the electrons. So in a carbon atom, 6 protons, that's 6 positives, and 6 electrons, that's 6 negatives. Positive 6 plus negative 6 equals 0. And it's the same way for every atom when the atom is by itself. That changes, and we'll see why and how, as atoms start to combine with each other a little bit later on. Not too long from this chapter. Ready? Mass number. I mentioned this a little while ago. The mass number is the number of protons plus neutrons. Protons will always be the same. Neutrons can vary. The mass number does not have a unit, and that's because the mass number is not a measurement such as 25 kilograms or 10 meters per second or 65 ounces or 28 newtons. The mass number is simply counting 1, 2, 3, 4 as we add up protons and neutrons. So the mass number of the carbon atom is 6 protons plus 6 neutrons equals 12. 6 plus 6 is 12. Now, a carbon 12 atom will be the 6 plus the 6 to give us a 12. But look here, 6 protons and 7 neutrons are going to give us carbon 13. And that's because 6 plus 7 is 13. Remember, neutrons can vary. Most carbon atoms will have a total mass of 12 because they have 6 neutrons. But carbon 13, there's an extra neutron there. What do you think about carbon 14? Well, remember, protons never change, so the P will be 6. So how many N's will there be? Well, carbon 14 comes from 6 protons plus 8 neutrons. That's a total of 14. Had a mistake there, but I corrected. 6 P's plus 6 N's give us the total mass of 12. Notice that we write the element name hyphen mass, and that's going to distinguish carbon 12 from carbon 13 from carbon 14. Most atoms will vary in neutrons, and as we go further into the periodic table and the atomic numbers get higher, the mass numbers are going to get higher and higher and higher as well. There are exceptions, though, where the mass of one atom is slightly lower than the mass of the atom before. But in general, the pattern is as atomic number increases, so does the mass number. But there are a few exceptions to the mass number. Oh, forgot to ask if you were ready. Isotopes. This is what we call the same atom or element, but the atom has a different number of neutrons. Therefore, that carbon 12, remember, that is 6 protons and 6 neutrons. We have carbon 13, 7 neutrons, and then we have carbon 14 with 8 neutrons. These are 3 different isotopes. Again, that's because we have 6 neutrons here, 7 neutrons here, and 8 neutrons here. So the word isotope means that the number of neutrons has varied. Neutrons will make that atom a little bit heavier or lighter if missing a couple of neutrons. Another example, sulfur may have 16, 17, or 18 neutrons. Well, sulfur has 16 protons. All sulfur atoms have 16 protons. Therefore, with 16 neutrons, that's a mass of 32. And then with 17 neutrons, that's 33. And with 18 neutrons, that's 34. So I would write these as sulfur 32 or 33 or 34. And then I simply subtract, let's say 34 minus 16 to get the 18 neutrons. And we'll do some practices with that. The isotopic notation we're going to see on the next page, but also page 59 of the textbook. This shows that both the atomic mass and the atomic number, and then we can figure out how many neutrons that isotope has simply by subtraction. And we're about to see some examples of that. Isotopic notation will give us both the atomic mass and the atomic number, or the mass number and the atomic number. You can say it either way. Ready? All right, now look at the screen here. The x, just like in math, x can mean any element, like x can mean any number in math. And you look over here, capital A, top left, that's the mass number, neutrons plus protons. We put the atomic number here, Z represents atomic number. That's why earlier when I wrote the calcium, I put the 20 down here. Calcium atoms that have 20 neutrons have a total mass of 40. That's going to be 20 protons plus 20 neutrons. Now, these are not always going to be the same. In fact, for most atoms, these will be different. But for calcium, most of those atoms do have 20 neutrons. You see neon right here has an atomic number of 10 protons, but a total of P plus N equals 20. That means 20 minus 10, that's 10 neutrons for an atom of neon. Takes some practice to get used to, but look at the neon 22 over here. Atomic number of 10, bottom number. Top number is a total mass. Well, atomic is 10, so how many neutrons in this atom of neon? 22 minus 10, and already looks like a little kid subtraction problem. 12 neutrons for an atom of neon 22, an isotope. All right, let's look at some more. The top left is the mass number, okay, just like right here. That's a total mass, so when we say neon 20, we have element mass. We write the symbol here, we put the mass there. The bottom left is the atomic number. All neon atoms have 10 protons. That's why neon is element number 10. That goes on the bottom left and always on the left side. The neutrons is, I just showed you, the mass number up top minus the atomic number down on bottom. So once again, how many neutrons does neon 20 have? That's a perfectly legitimate test question. All you have to do is this. Set it up like a little kid subtraction, and neon 20 has 10 neutrons. Neon 22, do the subtraction. Neon 22 has 10 neutrons. That's really all there is to it. Ready? Isotopes also help give atoms some of their physical properties. The isotopes of the same atom might have some different properties, such as the carbon I mentioned a little while ago. Carbon-12 is very stable, very safe. Think of charcoal, that's carbon right there. The pencil lead you might be writing with, that's not lead. That's actually a form of carbon called graphite. Very stable, very safe. Carbon-14 has a couple of extra neutrons which might give off some radioactive nuclear energy from the nucleus. Now, there aren't that many carbon-14 atoms in comparison to carbon-12. Most carbon atoms are carbon-12, 6 protons, 6 neutrons. But I'm just showing you here that the difference in neutrons could make the atom a little bit unstable, which means able to give off nuclear energy. Ready? Yeah. An ion is actually something we're going to deal more with in a little bit later chapter when we talk about combining the atoms, but we'll define that now. These are atoms with an electric charge. Remember, all atoms by themselves have a neutral charge because the protons equal the electrons. An ion has either gained or lost electrons. Therefore, that atom has gained either a positive or a negative charge depending on whether or not the atom has gained or lost some of its electrons. That's going to come in more detail later on. I'm just giving you the definitions right now. An anion has gained electrons, a negative charge. Non-metals, those are on the right side of the periodic table, actually to the right side of the staircase. They tend to add on electrons. Therefore, they have more negatives than they do positive. That's going to give us a net negative charge. For example, chlorine, when combined with sodium, chlorine will gain an electron. That means chlorine now has a charge of -1. Here's a metal that will give away electrons, coming up right here. The magnesium. A cation is an atom that has lost electrons. Metals will do that. Metals are to the left of the staircase, so there are many metals. Most of the elements are actually metals. A cation is a metal that has lost electrons. Magnesium will give away 2 of its electrons. It's 2 valence electrons. Again, why and how coming later on. But that magnesium atom now has 2 fewer electrons. Started with 12, gave away 2. Magnesium now has 10 electrons total, but still 12 protons. -10 and +12, that's +2. And all that's coming up later on. I'm just giving you the definition of an ion now. Ready? Atomic mass, remember when we did the mass number, we simply added up the protons and the neutrons. But if you look at the periodic table, you see the mass written as a decimal. Must be a reason for that. In most of the boxes on the chart, that mass is a decimal. Here's an example. We mentioned carbon-12, 6 protons, 6 neutrons. However, the mass on the chart says 12.01, or a different chart may be rounded to the 3rd or even the 4th decimal place value. Why is that? Well, remember, isotopes vary in how many neutrons. Therefore, if we add up all of the isotopes and then divide by how many there are, we find an average, we're going to get a decimal. And when we measure atomic mass, we use the unit called the atomic mass unit, which can be just a U, lowercase, or AMU, lowercase. Now I look at that 12.01 right here. This tells me something. Since most carbon atoms have 12 total masses, protons plus neutrons, that average is above. That means there have to be some atoms with extra neutrons. There may be some missing neutrons, but there are going to be more that have extra neutrons than there are too few neutrons. That's going to skew the average up a little bit. It's like taking your test grades and you end up with, let's just say your average test grade is 95.2. Now we may say 95 in the grade book, but you got a 0.2. That means you have scores that are higher than 95 that pull the average up very slightly by that 0.2. You might have 1 or 2 lower than 95, but more likely you have scores above 95 to raise that average to 0.2. Round off the decimal to get the mass of most of the atoms of that element. So I look here and I see that carbon rounds off to the whole number 12. That means most of the atoms of carbon will have a mass of 12, 6 protons plus 6 neutrons. Most carbon is carbon-12, but we saw earlier there's carbon-13, there's carbon-14, and there probably are other mass after the hyphen with carbon as well. Okay, but most carbon is going to be carbon-12, and again, that means 6 protons plus 6 neutrons. And that will happen with pretty much all the atoms. Ready? That is all for this set of notes, 3B. Of course, there's a lot more about the periodic table coming your way over the next few chapters. Thank you.